Welcome to the CWI Deep Dive podcast series. This is one episode in a series of 11, each covering a chapter of welding inspection technology. These deep dives are designed for inspectors preparing to take the American Welding Society Certified Welding Inspector exam. They are not meant to replace enrolling in a Certified Welding Inspector preparation course or dedicated self-study, but really to complement them. Along with our CWI Part A Test Prep app available on the Apple App Store, these discussions will help strengthen your preparation. You can continue learning at work, during your commute, or, wherever you find time. Today's deep dive is brought to you by AMS Level 3, providing consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. Learn more at the link in the video description.
And just a reminder, this discussion is an independent educational discussion based on concepts from the American Welding Society's Welding Inspection Technology book. We are not affiliated with the American Welding Society, and this isn't a replacement for purchasing or studying the original text. Our goal is simply to provide commentary, explanations, and reinforcement to help inspectors like you prepare for the CWI exam.
Okay, let's unpack this. We're dedicating this deep dive to Chapter 3, focused on weld joining processes. Now, fusion welding is clearly dominant on the CWI exam, but our source material really stresses that an inspector needs a comprehensive grasp of all metal joining methods. Why does the CWI candidate need to know about, say, resistance welding or soldering when they're usually checking SMAW?
Yeah, that's a great question. It really boils down to early discovery and, frankly, cost prevention. If you, as the inspector, understand the inherent operational advantages and limitations of every process, you can spot potential problems in process, not just waiting for a final NDT report, catching an issue when the component is just starting out. That's drastically cheaper than grinding out a massive repair after the entire fabrication is complete.
That economic incentive is powerful, definitely. And our study notes highlight that understanding the equipment itself, the power sources, the wire feeders, is mission critical. Because discontinuities often occur as a result of, equipment deficiencies.
Absolutely. If a GMAW machine isn't maintained properly, the weld's going to suffer. Simple as that. But there's a huge personnel component, too. It's not just the machine. Having some hands-on knowledge, or at least a strong theoretical grasp of the process you're inspecting, it earns the cooperation and respect of the welders. And that collaboration, that's the foundation of effective quality control. They're much more likely to bring an issue to you if they respect your technical opinion.
Right. Good point. Okay, before we dive into the 8 major AWS groups, let's make sure we're speaking the same language. What is the technical definition of a weld?
Okay. An AWS weld is defined as a localized coalescence of metals or nonmetals, produced by heat or pressure or both, and importantly, with or without filler metal.
So that distinction is critical. Coalescence. The material has melted and grown together, becoming one. That's key. The process of fusion is paramount. Got it. Now, let's get into the heavy hitter for the CWI exam, the industry's original workhorse. Shielded metal arc welding, SMAW.
Right, SMAW, or stick welding, as most people know it. It operates by creating an electric arc between the base metal and a covered electrode. That arc melts the electrode, the base metal, and the coating, forming the weld pool. Pretty straightforward concept.
But that electrode coating, the flux, it's really doing the heavy lifting here, isn't it? Beyond just providing filler metal. Our notes highlight 5 critical functions. In your experience, which one is maybe the most important for an inspector to understand when looking for potential weld quality issues?
That's tough. They're all important. But I'd probably lean towards the function of insulating. Yes, the flux provides the initial gaseous shielding, which is vital, and it gives you that deoxidizing and cleaning action in the puddle, plus some alloying and ionizing for arc stability, all critical. But after the weld is done, that solidified slag blanket's job is to insulate the weld metal, slowing down the cooling rate. If that slag cover is inadequate, or if the welder chips it off way too quickly, the weld cools too fast. And that can lead to microstructure issues or even cracking, especially with some high-strength steels.
Ah, that insulation detail. That's a great practical takeaway. Okay, let's tackle the famous classification system for carbon and low alloy steel electrodes. EXXXX. What do those first, say, 3 digits tell us that's essential for an inspector?
Okay, they define strength and position. The E just means electrode. That's easy. The first 2 digits, or sometimes 3 for higher strength rods, they specify the minimum tensile strength of the deposited weld metal. It's in thousands of PSI. So, for example, E70 means 70,000 PSI minimum tensile strength. E110, 110,000 PSI. Then the next digit tells you the welding position. One is all position flat, horizontal, vertical, overhead. 2 fig is only for flat position and horizontal fillet welds. And 4 is specifically designated for downhill progression, like in pipeline welding.
I noticed position 3 is never used. That seems like a random detail, but I guess it's good to know it's skipped. Now, storage. This is where a lot of compliance issues seem to pop up, especially with low hydrogen electrodes. What's the mandatory storage requirement for those rods ending in 5, 6, or 8?
Oh, this is critical. They must be stored either in their original hermetically sealed containers, unopened, or once opened, immediately transferred to vented, heated holding ovens. And those ovens have to maintain a minimum temperature of 250 degrees Fahrenheit. No exceptions. The reason is simple. Moisture contamination introduces hydrogen into the weld metal, and hydrogen is the primary cause of delayed cracking, or hydrogen-induced cracking. Big problem.
Right. Okay, let's look at the power source then, because SMAW runs on constant current, CC, and it uses what they call a drooping volt-amp curve. For someone prepping for the CWI exam, why is understanding that drooping curve, theoretically essential to understanding weld quality?
Yeah, it's highly counterintuitive, which, makes a perfect exam material. When the welder increases, the arc length pulls the electrode further away, the electrical resistance across that arc gap shoots way up. Now, the CC power source's drooping curve dictates that the voltage increases sharply to compensate maybe up to 32%, even though the actual current only drops slightly, maybe 10%. So that sharp rise in voltage means a longer arc is actually hotter in SMAW. More voltage, more heat.
Wow, okay. So if an inspector walks up and sees a welder running a noticeably long arc, that should instantly flag not just poor technique, but potentially excessive heat input, which has its own set of problems. That immediately brings us to discontinuities. SMAW is kind of notorious for two main problems: porosity and arc blow.
Correct. Porosity is usually technique-related, like running too long an arc, like we just discussed, or using moist, low-hydrogen electrodes that weren't stored properly. Arc blow, that's a different beast. It's a magnetic field distortion issue. It really plagues direct current, DC, welding, especially when you're welding near edges or corners or big changes in the part's contour. The magnetic field gets all bunched up.
Okay, so what are the top, say, 3 practical solutions an inspector should recognize or maybe suggest to reduce arc blow on the shop floor?
All right, number 1, if possible, switch from DC to alternating current, AC. The rapid switching disrupts the stable magnetic field buildup. Second, advise the welder to hold the shortest possible arc length. Less distance, less deflection. Third, changing the ground clamp location can sometimes help redirect the magnetic field. Or even wrapping the work cable around the workpiece a few times in a direction that sort of neutralizes the field. That can work wonders sometimes.
Excellent. Practical tips. Okay, if SMAW is the workhorse, let's move to the marathon runners, the high productivity processes: gas metal arc welding, GMAW, often called MIG, and flux cord arc welding, FCAW. How does GMAW differ fundamentally from stick welding?
Well, GMAW uses a solid wire electrode that's fed continuously from a spool, no stopping to change rods, and the shielding is provided externally by a gas, which might be inert like argon or maybe active like CO2 or a mix, and crucially, it relies on a constant voltage or CV power source, not the constant current CC used in stick. That's a huge difference.
What's fascinating, you mentioned this, is how the CV power source makes GMAW semi-automatic. It almost manages itself in a way.
It's entirely about self-correction. Yeah, it's pretty clever. If the welder accidentally shortens the arc lengths, maybe their hand dips a little, the voltage across that shorter gap drops. The CV machine senses that voltage drop instantly and dramatically increases the current output. That surge in current automatically increases the melt-off rate of the wire, burning it back faster to reestablish the original stable arc length and voltage the machine was set to. So the machine automatically compensates for minor changes in stick out or arc length.
Clever.
Yeah.
Okay, GMAW has 4 basic metal transfer modes. Which mode tends to cause the most inspection grief and why?
Probably short-circuiting transfer. It's great because it uses the lowest heat input, so it's good for thin sheet metal or out-of-position work. But it carries the highest risk of incomplete fusion or cold lap, especially on thicker base material if the parameters aren't dialed in just right. You really have to watch for that lack of penetration. Conversely, spray transfer uses the highest heat input, gives great fusion, but it requires a shielding gas with at least 80% argon for it to function properly.
Got it. So shifting gears slightly to FCAW flux cord arc welding. This process gives us those high deposition rates like MIG, but it brings back the benefits of flux, which is housed inside a tubular wire this time. And we have 2 main types: gas-shielded, FCAWG, and self-shielded, FCAWS.
Right. FCAW is a real beast for deposition speed and getting a lot of weld down quickly. And that self-shielded wire, FCAWS, is often preferred for field work since it handles wind much better than purely gas-shielded processes like GMAW or GTAW. The flux generates its own shielding. But there's a major trade-off, especially for the inspector. Maintaining quality requires maintaining a fast travel speed, consistent and fast.
Why is that speed so critical here? Is the primary risk in inspectors looking for something like slag inclusion?
Precisely. That's the main danger. If that travel speed drops, even just for a second, the molten slag created by the core flux can physically roll ahead of the advancing weld puddle. It gets trapped under the solidifying weld metal, and boom, you have a definite rejectable slag inclusion. You have to keep moving to stay ahead of the slag. This process also produces significantly more smoke and fumes compared to GMAW, which is an important occupational hazard consideration as well.
Okay. Moving now to the precision and high-quality processes. Gas tungsten arc welding, GTAW, or TIG as many call it. The key feature here, of course, is the non-consumed tungsten electrode.
Exactly. GTAW is really the go-to process for high-purity applications, aerospace, nuclear work, things like that. It uses an inert gas, usually argon or helium, for shielding, and there's zero flux involved. That means absolutely no slag is produced, which leads to exceptionally high-quality, clean, precise welds. You add filler metal separately if needed.
We have options here for current, DCEN, or AC. What's the practical implication of choosing one over the other for a specific material? Like, why use AC for aluminum?
Good question. DCEN, that's direct current electrode negative, means the electrons flow from the tungsten to the workpiece. Most of the heat, maybe 70%, is focused deep into the plate. This results in deep, narrow penetration, and it's typically used for things like carbon steel, stainless steel, titanium. Alternating current, AC, is crucial for materials like aluminum and magnesium. These metals form a tough, refractory oxide layer. The AC cycle provides a necessary cleaning action during the electropositive half cycle that effectively sandblasts or busts through that oxide layer, allowing for good wetting and fusion. It gives you more of a medium penetration profile compared to DCEN.
This raises an important question then. What is the primary discontinuity that is pretty much unique to GTAW, and how can an inspector spot the potential cause?
That would be tungsten inclusions. Since the electrode isn't supposed to be consumed, these hard, brittle metal fragments only get into the weld if something goes wrong. Usually it means the welder contaminated the weld pool, either by accidentally dipping the hot tungsten tip into the molten metal, or maybe touching the filler rod to the tungsten. Or they could simply be exceeding the recommended current limits for that specific diameter and type of tungsten, causing it to overheat, degrade, and fragments break off. Oh, and inadequate shielding gas flow or coverage can also cause the tungsten to oxidize and erode, leading to inclusions.
Right. Okay, next up is plasma arc welding, PAW. It's similar to GTAW, but features a constricted arc.
Exactly. That constriction is the key difference. It's achieved by forcing the plasma gas, usually argon, through a small copper orifice or nozzle inside the torch body surrounding the tungsten electrode. This creates a much straighter, more focused, more concentrated, and significantly more intense heat source compared to GTAW. It reaches extremely high temperatures.
And that concentration allows for that special keyhole welding technique, right? Why is seeing that keyhole a positive indicator for an inspector?
Yes, the keyhole technique is often used with PAW for making full penetration welds in materials up to maybe 38-inch thick, sometimes more, in a single pass. The intense plasma arc actually penetrates completely through the material, leaving a small visible hole, the keyhole, at the leading edge of the weld pool. Since the molten metal flows around this keyhole and solidifies behind the moving arc, actually seeing that keyhole is a positive visual indication that you are achieving 100% complete joint penetration. It's direct evidence.
But even PAW has its own unique potential problems.
It does. If the weld termination isn't handled correctly, especially ramping down the current to close the keyhole, you can get keyhole closure porosity trapped right at the end of the weld. And because the arc is passing through that copper constricting orifice, if the current is set too high or the nozzle gets damaged, you run the risk of picking up subsurface contamination from that copper nozzle being transferred into the weld metal.
Okay, now we get into some more specialized high deposition or unique applications, starting with submerged arc welding, SAW.
Right. SAW is the king of deposition rates for flat and horizontal work. huge amounts of weld metal fast. It uses a continuous solid wire electrode similar to GMAW, but it's completely submerged under a blanket of granular flux. The arc is totally hidden under the flux, which is actually a benefit for the welder. No arc flash, so often no helmet needed. But it's a limitation for the inspector, obviously, who can't visually monitor the pool during welding.
And that flux containment also dictates position, right? SEW can really only be done in positions that support the granular flux, basically flat or horizontal fillet positions. What is the key discontinuity specifically associated with SAW parameters?
Solidification cracking, often centerline cracking. This tends to happen if the welding parameters current, voltage, travel speed produce a weld bead with an extreme width-to-depth ratio. Either too wide and shallow, or sometimes too narrow and deep. Both can lead to segregation and stress during solidification that causes centerline shrinkage cracking as the weld cools. Bead shape is critical in SAW.
Then we have electrocycle welding, ESW. Our source material says it isn't really an arc process, except maybe just to get it started.
That's correct. After initiation, ESW relies on the principle of resistance heating. An electrically conductive molten flux puddle, or slag bath, is maintained between the base metal edges and the filler wire, or guide tube. The current passing through this resistive slag generates intense heat, which melts the base metal edges and the continuously fed filler wire. It's more like a continuous casting process in the joint. ESW is used pretty much exclusively for joining very heavy sections, often 34-inch thick and much, much thicker, usually in a vertical progression. However, interestingly, due to the position of the electrode relative to the molten pool, the official welding position is still technically considered flat for coating purposes. A bit counterintuitive.
Since ESW kind of resembles a casting process, what are its inherent problems that an inspector really needs to look for?
Two main concerns. First, centerline cracks can still occur due to the large volume shrinkage as that massive weld solidifies. And second, perhaps more critically, the very slow cooling rate inherent to the process leads to significant grain growth in both the weld metal and the heat-affected zone. This coarse grain structure can seriously degrade the mechanical properties, especially toughness, of the joint. Post-weld heat treatment is often essential.
Right. Okay, moving to the high-energy beam processes. Laser beam welding, LBW, and electron beam welding, EBW. These both produce unbelievably deep, narrow welds.
They really do. Very high depth-to-width ratios, often greater than 10:1, are common. Think deep and skinny welds. EBW, especially when it's performed in a high vacuum environment to prevent electron scattering, is incredibly powerful. It can make single-pass welds up to maybe 4 inches thick in steel. The trade-off, though, is immense. These are very high-cost processes requiring sophisticated equipment, and they demand absolute, extremely accurate joint positioning and fit-up. If that narrow, high-energy beam is off by just a hair, it completely misses the joint.
Wow. Okay, stud welding, SWD. Seems pretty straightforward. An economical and effective method for attachments, like shear connectors on bridge beams. How does an inspector typically confirm a good stud weld without needing something like X-ray?
It's usually a combination of visual and physical checks. Visually, you must confirm the presence of a complete 360-degree reinforcing fillet of expelled metal, often called the flash, around the base of the stud. That indicates proper fusion and upset. Then, often, a simple yet effective physical test is performed, like a hammer test or bend test depending on the code. For the hammer test, a good, solid stud weld will typically produce a clear ring when struck sharply near the base. A poor or incomplete joint, maybe lack of fusion, will often produce a dull thud. Simple, but it works.
Makes sense. Finally, resistance welding, RW. This uses electrical current and mechanical pressure, but no filler metal or flux. Primarily used for joining sheet metal, like in automotive bodies, using resistance spot welding, RSW, or resistance seam welding, RSEW. What are the common causes of inadequate shear strength in an RW spot weld nugget?
It usually boils down to a failure in one of the three key parameters: time, heat, current, or pressure. The shear strength of the weld nugget formed between the sheets will likely be inadequate if the welding amperage current is too low to create sufficient heat, or if the clamping pressure holding the pieces together during the weld cycle is too low, or if the duration, the time the current flows, is too short. Any of these can result in an undersized nugget or non-fused areas at the fang surfaces where the sheets meet.
We'd also like to recognize Skaggs Media LLC as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com.
Okay, our final category covers the lower temperature joining processes, starting with oxyacetylene welding, OAW. Right. OAW is really a chemical welding method, using the heat from burning acetylene gas with oxygen. Acetylene is the only common fuel gas that gets hot enough for effective fusion welding of steel. Other gases like propane are great for cutting or heating, but not really welding steel. And interestingly, the flame itself, when adjusted properly, provides its own shielding envelope of combustion products, meaning no external flux is typically necessary for welding steel. Oh, and a key safety note for CWI candidates. Pure acetylene gas becomes unstable and shock sensitive above about 15 psi pressure. That's why those cylinders aren't just empty. They're filled with a porous material soaked in acetone, which dissolves the acetylene and keeps it stable at higher storage pressures.
Good safety tip. Now, brazing. Here, the base metal does not melt, only the filler metal does. What temperature is the dividing line that separates brazing from soldering?
The magic number is 840 degrees Fahrenheit, or 450 Celsius. Brazing uses a filler metal that melts above 840 degrees Fahrenheit, but still below the melting point of the base metals being joined. The key mechanism here isn't fusion, it's capillary action. The molten filler metal is drawn or pulled into the very tight space, the joint gap between the two closely fitted surfaces, like water being pulled into a narrow tube.
Okay, so if capillary action is the driving force, what two critical variables must an inspector ensure are correct to get the required joint strength in a brazed joint?
Number one is cleaning. Cleaning is absolutely paramount. Any oxides, grease, dirt, any contamination on the surfaces will instantly stop or significantly reduce the capillary action. The filler metal just won't flow or wet properly. And number two is the joint gap. Brazing relies on a very minimal gap, typically specified as maybe 0.01 Eller inches or even less, often just a few thousandths of an inch. That tight clearance is what maximizes the capillary pull and ensures the joint fills completely for full strength. Brazing's superpower, really, is its ability to join dissimilar metals, like copper to steel, or even metals to nonmetals, like ceramics in some cases, provided that capillary action can work.
Right. And soldering is essentially the same capillary process then, but the filler metal melts at or below 840 degrees Fahrenheit. The key difference seems to be the reliance on flux.
Exactly. While brazing sometimes uses flux, soldering almost always requires it. In soldering, the flux's primary job is to chemically remove any existing oxides from the base metal surfaces and prevent them from reforming during the heating process. This chemical cleaning action is crucial for improving the wetting and flow of the lower temperature molten solder, ensuring that capillary action is effective in pulling the solder into the joint.
Wow. We've covered an incredible spectrum of joining methods today, haven't we? From manual stick welding out in a field somewhere all the way to automated high-energy beams in a vacuum chamber. I think the key takeaway for any CWI candidate listening has to be that understanding the limitations, and maybe more importantly, the potential discontinuities typically associated with each of these processes. That's where true inspection mastery lies. It's really about knowing where the failure points are likely to be found for each specific method.
I totally agree. And if we connect this to the bigger picture, given this huge range of processes we discussed, each with its own speed, cost, complexity, skill level required, maybe the single greatest variable in overall quality control becomes maintaining consistent standards across multi-process fabrication sites. You might have SMAW, FCAW, and SAW all happening on the same large project. So for your next step, maybe consider how different codes, like ASME or AWSD 1.1, might actually impose restrictions on which process choices you can even use. For instance, they might limit something like resistance welding for certain critical structural joints versus requiring a full fusion process like GTAW or SMAW, depending entirely on the criticality and the thickness of the application. The code often dictates the allowed processes.
That's a fascinating thought to end on, tying process selection and its limitations directly back to code compliance and application criticality. Great point. If you find these deep dives helpful, please consider buying us a cup of coffee. Your support truly means more than you know. By subscribing, you're helping cover the costs of the tools and subscriptions we rely on to create and share these non-destructive testing videos. Every contribution goes directly into producing content that educates, mentors, and supports technicians out in the field. Thank you so much for standing with us and making this possible.
And before we wrap up, just a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting services, NDT training and mentorship, or help with compliance solutions like NADCAP or Federal Aviation Administration readiness.
To learn more, visit amsl3.com, and don't forget to follow our YouTube channel for more insights and updates on non-destructive testing. We'll see you on the next deep dive.